So there is a quiz review tonight. Well, first of all, of course, there's a quiz on Friday. It happens in your recitation section, so it's a 50-minute quiz. It's closed book, but you can bring a calculator if you wish, although we're always happy to accept a formula instead of a number if you prefer to write that down. I always encourage everybody to show their work because we can't really give partial credit to a wrong number, but we can give partial credit to work which shows you know what you're doing that has a trivial mistake in it. So, if you have a chance to show your work. There is a quiz review tonight, 7:30 to 9, in 34101, which is the big auditorium over in building 34. If you can't make it to the quiz review, there are quiz review videos, which are basically the same sort of problem solving that are available on the course website on the handouts page. So you can use those, or use both, whatever is good for you. The lab checkoff is due this Wednesday evening. Look at the lab hours. If you haven't yet got a checkoff for lab 1, you have to do it before the end of lab hours on Wednesday. We can't check off everybody at the last minute, so if you still need a checkoff, maybe stop by later today or during the day tomorrow so that we don't have a big crunch at the last minute on Wednesday. Any questions about the upcoming quiz? What's on it? Yeah. Okay. So today we're going to talk about how to give you a way of thinking about how to create designs for sequential logic. So we have our new machine, our new sequential logic machine, consists of combinational logic, which we've studied now for several lectures, which basically computes output values based on the current values of its inputs, the instantaneous values of the input. So whatever the values are in current state in the input wires will become the values on the output of the combinational logic cloud after the propagation delay of the combinational logic. What we added to our system was the notion of being able to save what we call the state. And the state is really an encoded binary value, in this case a k-bit binary value. These little slashes across the wires with a number next to them, or in this case a symbol, represent a signal, a multi-bit signal. So this is basically saying this signal is k bits wide, or this signal is m bits wide. That's what these little bus annotations mean. So a wire on the diagram which carries more than one signal is called a bus. So we have an m-bit bus here and a k-bit bus there. This is basically a k-bit state registers, or k 1-bit registers in parallel. That's what this represents. And that's remembering whatever it is we want to know about the current state of the machine. It captures sort of anything that we want our machine to remember about the previous history of the inputs. And the way this works is that, the combinational logic is acyclic graph at a base, the static discipline. Once you give it a set of valid inputs here, after TPD, it will guarantee a set of valid digital outputs there. And we can, of course, describe the operation of this combinational logic with a large truth table. We'll need, if we have k plus m inputs, we'll need 2 to the k plus m rows in our truth table. And we'll need something that describes for every possible combination of inputs, for the 2 to the k plus m combination of inputs, we'll need k plus n output values. Right? So for every possible combination of input, we'll have to specify the k next state outputs and the n values for the n outputs. Okay, and then over here we have where we, carefully using our little feedback mechanism, our positive feedback that we build into our registers to provide stable storage. It only works if we guarantee that we meet the setup and hold times in the input here. We'll talk at the end of the lecture what happens if we don't meet the setup and hold times. But typically, when everything is under our control, we'll design our system so that, in fact, we do meet the setup and hold times to guarantee correct operations. And this remembers k bits of information. And so that means there's 2 to the k possible unique states. So if a particular combination of bits in the state register represents one state, there are 2 to the k such states available to us. So let's see how we're going to use this machine, and we're going to basically introduce a new abstraction that will let us do it. Our running example, at least for the next couple of slides, is a digital combinational lock. And what we'd like to do is, is a sequential circuit. So inside there's some registers and some combinational logic. This particular circuit has a single output U unlock, which should be equal to 1 when the user has correctly entered the combination. The way the user entered the combination is with the appropriate setup time, you put the next digit of the combination here, and at the rising edge of the clock, the digital combinational lock will read the input value, the value of the next bit of the combination that you're putting in, and decide whether or not you've met the criteria, which is that the last 4 inputs, so over the last 4 clock cycles, you've entered the digit 0, 1, 1, 0. So the reason that this is sequential logic is that we have to remember something about the input values that have come from the past. That's what's being remembered in the state of this machine here. How many state bits do we need? Well, we'll find out in a moment. But whenever we're designing sequential logic, we're going to have state that remembers everything we need to remember about the inputs. So let's go about designing this piece of logic, and then I think you'll quickly get the hang of what we need to do. Our abstraction is called a finite state machine, an FSM. And a finite state machine is really pretty simple. It's a machine that has a certain number of states, k states. We'll tell you how many states our finite state machine has. And one of them is designated the initial state, the state that once you turn on the machine, is the state that you start at. There are m inputs and n outputs, typically small numbers, although they can be quite large. And what we do to describe the operation of the FSM, of the finite state machine, is we provide a set of transition rules. So for each possible internal state, so for S1 through SK, we're going to provide some rules that tell you for the current value of the inputs, so we're going to tell you the next state for the machine. In other words, at the next rising clock edge, how the internal state will be updated. So S prime is a function which is the new state, or the state that will become the current state of the machine after the next rising clock edge, is a function of its current state plus the current values of the inputs. Okay, so that's the transition table. And then we'll also provide some output rules, which will tell you the value of each output given the current state that we're in. That's one type of machine. Another type of machine, the output values are a function not only of the current state of the machine, but also the values on the inputs. And so this is called a Moore machine, and this is called a Mealy machine, after Professors Moore and Mealy, I suppose, who sort of invented this terminology. In 004, all of our state machines, FSMs, will always have the outputs dependent only on the current state. Okay. So you can say, okay, that's a pretty abstract abstraction. How are we going to use it? So let's build a state transition diagram. So this is going to be a graphical representation of the transition table that's required of us for our lock. Okay, so we'll need an initial state. You can see it here. We're going to give it a symbolic name. I always give my states symbolic names. And that name tells me what that state represents in terms of what we've remembered from the input history. We also, because the outputs in this machine are a function of the current state, we basically associate them with the current state. So whatever state, as the machine will actually have multiple states it can be in over time, depending on what the sequence of inputs is. For each of those states, we'll specify the value that, in this case, the unlock signal has if the machine is currently in that state. Right? So when I'm in the state SX, which means I've seen none of the combination. I don't know, I've just turned on, I have no idea, the user has entered no part of the combination. So the X basically in this case means unknown. We want to say, look, I'm not going to unlock the lock for you, you haven't entered any combination bits yet. And the initial state will put an extra heavy circle around. Okay. Now, here's the first state in our state machine, and so let's understand what the diagram is telling us. First, this is another state, a different state, because it has a different name than the first state. It's S0. And what S0 is the state that represents what happens when the user has put in the first 0 in the combination. So we've seen one bit of the combination, we've seen that 0. And so not going to unlock yet because we have yet to see all the bits of the combination. And we transition from the SX to the S0 state if the user inputs a 0. Okay, and so we label these transitions with the value of the input. So this is basically saying if I'm in SX and I get the input value of 0, the next state that I'm going to go to is S0. Okay, and so here there's more machine to draw here, but you can sort of see all the basics here. I've described a state. I've described what happens when I get a particular value of the input, and I've described for each state what the value of the output should be. Okay, what I'm going to do is finish entering all the states that are necessary to sort of get the lock to unlock if I enter the correct sequence of bits, 0, 1, 1, 0. Now notice what I've done is I have a separate state that sort of shows the accumulated history. So in this state, I've seen the first 0. In this state, I've seen 0, 1 of a combination. In this state, what I want the machine to remember that it's seen 0, 1 once, and it's seen the first 3 bits of the combination. And in this state, I want to indicate that I've seen all 4 bits of the combination, and hence the unlock signal is 1. Okay, now there's lots of other things I need to fill in, which I'll do with a single stroke of the pen here. And I have to, for example, I have to basically describe for every state what happens for all possible inputs. So here's an example. When I'm in the unknown state and the user enters a 1, I still haven't seen any valid bits of the combination. A 1 is not a legal first digit of the combination. So I basically say if I'm in this state and the input is a 1, then I'm still in the SX state because there's nothing, I haven't seen any part of the combination yet. And so what I need to do is to identify for all the states, I should have a transition for a 1 input and a transition for a 0 input. So I can fill all those in here. And here I claim that this is a correct representation of the functionality of the lock. There are a few things that are a little perhaps puzzling at first glance. For example, why when I'm in this state and I get a 0 do I go back to that state? So I've unlocked the lock. I've seen the bits of the combination. Why is it when the user comes up not knowing the door is unlocked and starts entering a 0, why do I not go back to here? Why do I go to S0 instead? Yeah? Because you've entered a 0 and started 0. Right. The user not knowing has entered the first bit of the combination. What about when I enter a 1, why do I go to that state? Yeah? You've already entered 0, so right, so remember the definition of the lock is that the last 4 bits were 0, 1, 1, 0. So at the time the lock is unlocked, and so I've seen that. And so if I enter a 1 at this point, you can see that I actually have I've got the first 2 bits of the next entry sequence. So in fact, this sort of is a careful definition. This is sort of following the actual rules here very carefully. Now, often when you're designing a state diagram like this for a fancy piece of sequential logic, whether it's a traffic light controller or the sequence of operations necessary to cause, the SpaceX booster to come and land on its floating rocket pad at the end. Everything, all these pieces of digital logic are very complicated sequential machines, FSMs, and typically you have to call up the company and say, wait, I'm in a certain situation here and this happens, what should I do? Because they haven't completely specified the right operation yet. Sometimes it's obvious, sometimes it's a design choice. Okay, so everybody get does everybody feel comfortable with this diagram as a way of describing the operation of the lock? Yeah?
Why did it look at the last 4 digits? Why did it decide to just look at the last 2 digits?
Well, so the reason I have to have some memory about 4 is that there's a 4-digit combination, right? So if I only remember the last thing you've entered, if that's the only knowledge I have, I can't tell whether you've entered the earlier bits of the combination or not.
Why is it but this time it seems like it's just looking at the last 2 as opposed to the last?
Well, so this had to do with a sort of screwy definition of the lock. I mean, perhaps a better lock would have been once you're unlocked, okay, at the next clock edge, go back to unknown, so the user has to enter the combination from the beginning. In this case, the thing was, if the last 4 digits were entered without any particular knowledge of whether the same person is entering them or not, we would want to accept. If somebody's unlocked the door and I enter a 1, then from the lock's point of view, it's seen a 0, 1 as the last 2 digits of the combination. And you could argue that that's not does not build the lock that way. And that would make sense. So as I say, part of what you need to do when designing an FSM is to sort of sort out what's sensible in terms of what should the lock do in all these situations. Yes? Well, so what happens is that so here the lock is unlocked, right? If I enter a 1 here, I go back here and the lock is locked now, right? So the lock is locked and won't go back into the unlocked state until I finish entering in 0 and 1. At that point, 1 and 0, and at that point the lock will unlock again. Okay, so electronic locks, always try the door first and then enter your combination, just in case it was a dumb lock. Okay, so there are some rules that will help us understand whether the state transition diagram we've created is in fact well formed. So here's a picture. This is what a Moore machine would look like. Here we have the outputs, associated with each of our states, and then there's transitions shown from each state. If I'm in S3, I get a 0, I go to S2. If I'm in S3 and I get a 1, I go to S1, so forth and so on. This is a different diagram of a machine that behaves very much the same way, but this is called a Mealy machine. And what we've done is we've used a notation where we have the input values, just like we did here, but the output values are not associated now with a particular state. They're associated with a particular state and the current input value. That's what it means to be a Mealy machine. So we show the outputs on the transition arcs, not in the states themselves. We'll always use these. To check that a diagram is well formed, first of all, we have to make sure that all the choices of transitions leaving a particular state are mutually exclusive. In other words, every arc has a unique label. So there's not 2 arcs labeled 0 here, leaving the S3 state, because then if you got a 0, it would be, the FSM wouldn't be able to tell which way to go. Should I take which one of these 2 transitions labeled with 0 should I take? So, theorists love to think about non-deterministic FSMs and things like that, but mostly engineers aren't interested in that. So we have this rule that basically you had better have non-conflicting sets of labels on all of the arcs leaving each state. And the labels have to be collectively exhaustive. Sort of like we are now. So collectively exhaustive, which basically is sort of just telling us that we had better account for all the possible input values. So just as it would be a mistake to have 2 arcs labeled 0 leaving the S3, it would also be a mistake not to have any arcs labeled 1, because then if we got a 1 input, we wouldn't know what to do. If your intent is that the machine should stay in its current state, then you need to explicitly put a transition that looks like that. If you get a 1 and you're in S2, the next state is the same state. There's no default stay in the same state. You have to show every possible transition. So those are the rules of being a well-formed state transition diagram. Okay, we can actually represent all the information in the state transition diagram as a truth table. And here we go. We basically have a table that for every possible current state and for every possible combination of inputs, we list what the next state is and this unlock signal. And remember, this unlock signal is only a function of the current state. Right, so these 2 zeros here reflect the fact that the current state is SX and are independent of the input value. Okay, so this is a truth table, and I hope you're beginning to see the handwriting on the wall here. With the truth table, we're able to turn that into combinational logic. Right, so the first thing we need to do is to actually assign, change our symbolic names into some sort of binary representation for the state. Here I've sort of arbitrarily just numbered the states 0, 1, 2, 3, 4 in binary. The choice of the actual binary encoding to use for every state influences how complicated the logic is that you need to design. If you're using a ROM, it's pretty arbitrary, but if you're using real combinational logic, you can sometimes simplify the logic a lot because the way the Carnot's map works out by a clever encoding, by choosing a clever encoding so that it minimizes the logic that you need. That's sort of by way of information, because by and large, we'll be happy embedding the information in this truth table into a read-only memory. Okay. Then we can take this truth table to actually build hardware. So here's what our hardware is going to look like. We're going to basically, so this truth table here has 16 rows, and we're going to need information of 3 bits, and what should come out of our ROM is 3 bits of next state and 3 bits of next state and the unlock signal. So we have 16 rows altogether. So our read-only memory will have 16 locations in it, and each location will contain 4 bits of information. 3 bits of next state and 1 bit of unlock signal. So this is a 16 by 4 ROM, and here's our state register, our 3-bit state register. And notice that we've marked these wires here as being basically 3-bit signals, each of those. This represents the current state, and then this represents the next state. Now sometimes people get a little nervous about seeing a register who seems to be, its output value is being used to compute its next input value. Isn't there some sort of circularity involved here? Pause. So either you're asleep, you're not nervous, or you are nervous. So if you're not nervous, that's good for you. You've sort of figured it out. If you are nervous, let me see if I can help you feel a little better about it. So remember how the register works. There is no path between the input and the output. No combinational path. No direct circuit that at any point in time information from here flows, to here, okay, just sort of combinatorially. There's no combinational logic path from the input to the output. So there is no cycle here. So the register is okay for a register to be both the beginning of information flow within a clock cycle and also the destination of that flow. So at the rising clock edge, a new value comes out here. We compute a next value, and at the next rising clock edge, that value then gets latched in the register and becomes the next current state. Right? So it's a sequence of states, and it's perfectly okay to compute the next state from the current state. In fact, we have to. That's what an FSM does. And this register is not going to get confused at all. I mean, it's designed to be able to latch as inputs, okay, in such a way. We do have to guarantee that we meet the hold time here. In other words, the fact that this value will start to change when we do the new latch, but this value has to stay stable for a certain length of time after the rising clock edge for this latch to work correctly. We do have to guarantee that we'll meet the hold time from this register output to that register input. So we do have to guarantee that, and we do that mostly because the contamination delay of the ROM will be long enough so that this won't start to change even though too soon, even though this value has changed because of the rising edge of the clock. Okay, so we assume that we're meeting the setup and hold times because we make sure the timing of in is correct so that we don't have any violations of the dynamic discipline for the state register. And as I said before, 16 locations, 4 bits each. Okay, so just to make sure we sort of understand what we're doing, what we have is S state bits, and so the state here, the current state, that's this value here on this wire, basically changes right after the rising edge of the clock. So we've only shown the rising edges of the clock, and right after the rising edge, we get a new state value. So this little lozenge means we're not really care whether it's ones or zeros, but this is when it's changing in here, and this is when it's stable. Sometime after the current state value is out and becomes a stable value, after the delay of the ROM, we get a new next state value. That's what this little lozenge here is. This is a valid computation, and so long we meet this is valid for the setup time of the state register before the next rising clock edge, that next state value becomes the value of the current state after the clock edge. So this sort of get a new current state, do a bunch of computation. At the end of the cycle, somebody has told me what the next state will be. That gets loaded into the register, and we start the whole process again and again and again. And what's sequential about this is that we're going through a sequence of states for each clock cycle. Each clock cycle brings us to a new state. So many clock cycles in a row will take us through a sequence of states. Few housekeeping issues. Okay, how do we get this machine to start? What happens if there's sort of garbage in the state register when we start? I mean, the FSM is going to unlock the lock or blow up the nuclear reactor or cause the rocket to take off, even though we're not, I just turned it on, I'm sorry, Elon. Wish we had initialized that state register. And so the answer is, yeah, well, that's the piece of hardware we have to take care of. Perhaps we have a little multiplexer that before the first clock edge, we have a little reset signal we use that basically forces an initial value in here. And then the reset signal goes low, and now the values of the next state are determined by the logic, but we forced an initial value here. So typically when you design a piece of sequential logic, you have to have ways of forcing the state, at least the state bits that matter, to known values. When we design our computer, or our beta, which is a big piece of sequential logic, we'll certainly agonize a little bit over how to do that. Okay. What happens if I had 5 states, but I carefully used a 3-bit encoding, which means there's 8 possible state encodings? What would it mean if the state register somehow got into one of the invalid encodings? And so first question is, how could that happen? Okay, so if everything is going well, we should never get a state encoding that's not 000 through 100. We should not find 101 or 110 or 111 as a possible state encoding. If you are like me and you're always a little nervous about, well, we should be pretty clear about what will happen, just shrugging our shoulders and say, I don't know what will happen. The engineers, you shouldn't build machines that do that. Google driving cars. Well, we didn't think that would ever happen, so the car just, who knows what the car does. You can imagine the California regulators go, what do you mean, who knows what the car does? So what you should do is to be sort of fail-safe. So typically you would go back in and you say, look, if I ever get to one of these illegal states, go to the unknown state in the case of our lock. I don't know how I got into the unknown state, but you should have probably some action for every possible combination of state bits, even if they don't mean anything in your encoding, just in case a cosmic ray happens and you end up there. Okay, choosing the encoding for a state. Well, we have a pretty big complicated piece of logic for our digital combinational lock, which depended on our particular choice of encoding. Here's something that involves 4 state registers instead of 3, so it's a little bit more expensive that way. But the combinational logic is vastly simpler. What I've done here is built what's called a shift register, in which I'm remembering every time I enter a new value, all the previously stored values move down the shift register 1 bit. So this represents the current value, or the most recently entered value, and then the one before that, and the one before that, and the one before that. And what I've done is come up with a simple way of remembering what the input values were, and here I built a very simple piece of combinational logic that is, says, oh, look, if the last values were, 0, 1, 1, 0, going backwards in time, so 0, 1, 1, 0, if that's true, then unlock the lock. So there are times when you can pick a way of remembering the state. Well, I've shown you the most general way with a state transition diagram. Here's a much simpler way of remembering the history and decoding it directly. So this logic is probably smaller and cheaper than the one I carefully drew. How you do it, part of the fun of engineering is, hey, wait, can I think of a clever way of doing this? And so this type of more or less direct encoding of the history using a shift register is actually often the simplest. And so it's one of the things that I always think about when designing state machines. I've spent a lot of my life designing state machines. I was out in the real world for 10 years designing integrated circuits for lots of different things, mostly the very first direct broadcast satellite set-top boxes. We did a lot of the chips inside of there for We designed the chips. They were actually sold by different companies, but we designed the chips for them. Lots and lots of combinational logic, lots of sequential logic. It was a lot of fun, but you spend a time saying, can I be a little bit clever? Is there a way I can make this machine more affordable or have a faster clock cycle for higher performance? Okay, so that's so FSMs are our way of designing sequential logic. In my outside life, if you came in, you'd find, tablets full of circles and arrows and me thinking about, okay, how does this FSM work? So it's a tool that I use all the time. Questions right at the moment? No. Okay. All right, if I showed you this diagram, what could you tell me about the number of possible states of this FSM? Yeah. 2 to the k, right? So there's k state bits, and every possible combination of those k bits is a different state. And so there's 2 to the k combinations of k bits, because each bit can either be 0 or 1. How about this machine? Well, the first machine has m states, and it's connected to a second machine with n states. How many, so I think of this now as a big sequential machine that has x inputs and z outputs. How many possible states are there of that machine, if I don't tell you anything more? M times n, right? Because that would represent all the different possible combinations of the first machine and the second machine, which were buried inside. Okay, suppose I give you a machine. It has 2 buttons, a 0 button and a 1 button, and you play around and you discover that some sequences of 0s and 1s cause the light to light, and some sequences of 0s and 1s cause the light to go out. Got it? Okay, so you say, okay, can you write the state transition diagram? Is there a systematic procedure you can go through that would basically let you explore? Anybody ever play the old game, Dungeons? It's a computer game or Zork or any of those things where, you're in this maze of twisty little passages all alike, and you're sort of wandering around trying to draw a little map of how to get yourself through this maze. Well, this is sort of the same thing. You're starting to draw circles and arrows, and you're trying to figure out if you can figure out the map. So the answer is, well, no. Because unless you know something about the number of states in the state machine, you can't be sure, right? Because if you know the number of states, you can be sure. But if you don't know the number of states, you don't know if you've explored the entire, state space of the machine. Because the machine may have more states and you just haven't been there yet. So here's something where if you push 1, the light goes on, and if you push 0, the light goes off. And if you keep pushing 1, the light stays on, and you keep pushing 0, the light stays off. And it looks, you keep experimenting, and so long you try less than 3 1s in a row, everything's working fine. But then here's a magic thing where you press the 4th one, and all of a sudden the light goes out. Right, so you can imagine that if I don't know anything about the number of states, I don't know am I done exploring yet or not. However, if there is a bound on the number of states, there is a systematic procedure for actually discovering the state transition diagram. Okay, so with the bound, and using this little corollary here, which basically says, look, in a k-state machine, any reachable state starting from the initial state can be reached in k steps, in less than k steps. Okay, so that's just sort of the fact is that transition diagrams are very expressive, okay, but unless there's a bound on the number of states, this notion of external behavior does not give us all the insights we need to for what the state transition diagram looks like, unless we know the bound on the number of states. There's also the notion of equivalent machines, 2 machines that behave the same. And so, if I showed you these 2 diagrams and asked you if they were the same or they were different, right? Well, you can see one has 5 states, one has 2 states, clearly different state transition diagrams. But from the outside world, there's no way to distinguish whether you had this machine or that machine. They behave the same. For every possible sequence of inputs, okay, each of these machines will display the same behavior. So we would call these two machines as equivalent machines. And as engineers, we prefer this one because it requires much less logic to build. So after designing a FSM, one of the things that I often end up having to do is wonder, can I make it a smaller FSM? Are any of the states equivalent? Okay, so we want the simplest equivalent FSM. So keep that in mind. Let's try a real example. Let's build this ant. Here's a robotic ant, which for some reason in 004 has 8 legs. I never quite... It always amused me that that was true, and I've never gone to edit the slides to only give it 6 legs. So this is an arachno ant, I guess. It has 2 antennae, left and right, and they're sensors. So they're basically, the sensor is L is a 1 if the left antenna is touching something, and R is a 1 if the right antenna is touching something. And we want to make our ant smart enough to get out of one of these connected mazes, so-called connected mazes. Anybody know the rule about getting out of mazes? You know, these types of simple mazes? Right hand on the wall. Stick your right hand on the wall and just keep walking and you'll get out. Now, if the maze has islands in it and things like that, that doesn't work, right? So if you go, if you've never had a, you know, you've always wondered what it was like to be in a real maze. The Davis farm, it's up in, you know, outside of 495. Some fall, you should go out there. They build this corn maze, okay? And the corn is much taller than you. It's in the fall, so the corn's quite high. You are maybe for the first time in your life in a maze that's truly a maze. And enough people go through that all the paths are equally worn, so there's no tricks, right? And so you're literally trying to find your way around this maze just as you might have done as a little kid. It's a lot of fun. You know, all the MIT types put their right hand on the wall and discover there's islands in their maze, so you can't get out that way. So, anyway, this is the first time that I was really ever sort of truly lost. I mean, in the sense, like, I have no idea how to get out of this maze. So, and so my 4-year-old, Daddy, we're lost. Don't worry, we'll think of something. They had a snack bar in the middle, so you could say, well, we're not going to starve to death. So. Okay, so let's build a state machine that will make our robo-ant work. Try the Davis maze. It's great fun. Okay, if you're lost, if you are an ant, so the ant can move forward, and it can turn left, and it can turn right. That's what the ant can do. So we want to build, so the 3 outputs are to tell the ant to go forward, turn left, turn right, and then the only inputs I have are my antenna. So if I was lost in the middle of nowhere here, what should I do? I'm off screen. Sorry. I'm lost in the middle. What should I do as an ant? Well, turning right and left seems a little silly, right? But so moving forward is sort of the only choice. So the action is we're going to go forward until we hit something. So we're in the lost state. The output is going to say move forward, and we're going to keep doing that until our antenna touches something. So if either the left antenna or the right antenna touches something, we're going to go to another state. Okay, meanwhile, if neither antenna is touching, keep moving forward. Okay, so now that some antenna has touched, one or the other or both, we're in a situation where we've run into a wall. So now what we want to do is to have the ant rotate itself until it's ready to do the right antenna to the wall, right? So what it's going to do is we're going to tell the ant, so here we are, rotate counterclockwise, that's what this state is. So we're going to have the ant keep rotating counterclockwise until neither antenna has touched the wall. So the theory is no matter how we bumped into the wall, we're going to turn so our right antenna has just left the wall. That's what the purpose of this state is. So as long as any antenna is touching, keep rotating counterclockwise, turn, 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 until we're just at the state where we're no longer touching. Okay, so now we're in a new state now where we think that we've aligned ourselves right next to a wall that should be just beyond the reach of our right antenna. That's, in theory, that's what this next state represents. Okay. Alrighty, so now we're going to just sort of bump down the wall. If we're this state, we're going to sort of turn forward and turn right and hopefully touch the wall. And then we're going to step back and go like this. And so we're going to keep bumping down the wall as we go. Okay, so here we go. We're in this state, wall 1. We're going to turn to the right and move forward. If our right antenna touches, that means we're back in. We're touching the wall again. So let's go think a little bit about that. And so what we're going to do is turn left and move forward. So we're sort of bumping our way down the wall. What happens, however, if we reach out, we come to the corner, we reach out, and it's not there? What does that mean? It means we found a corner. So what should the ant do? It just keeps turning right in the hopes that it's moving forward and turning right, and hopefully it will run into that wall. So we're taking care of what happens when you get to an outside corner. Inside corners, you just treat like, you bump into the wall and you just turn and, walk along with that wall to your left, to your right. Okay, so we keep going bump, 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 bump around the outside edge. So there you go. So this might even work. Here we go. Here's my ant. Oops, too fast. This is a slow ant. Okay. Being very careful, just like Mommy taught him. Okay, so this ant is this is the state machine, sort of encoded as a truth table. And this ant is basically, each state of the machine is telling it what it should do. And you can see the ant is slowly making its way through the maze. Okay, and in fact, it'll eventually, enough of the slow, painful, it will eventually come over here and get to the food and be happy and stop. Just like the corn maze. Daddy, we're saved. A snack bar. You've been here twice already, dear. I hope they have a bathroom in the snack bar too. Parents have a very odd view of life. Okay. Alrighty, so here we are. How many of you have ever been to Hampton Court? The castle of, I think that was Wolsey's castle. It's beautiful. It's outside of London, south of London. If you've never gone, it's fantastic. One of the things they have the Hampton Court maze. So think of all these drunken Englishmen staggering around this big hedge maze. Here's the ant here. We'll set him running. For some reason, the English lords did not know about the right hand to the wall. Dear sir, I can't use my right hand. It is holding the goblet. And you say, well, okay. Try that, Duke. Okay. So we'll come back to see how the ant is doing later. Okay. He's busy. Oops, wrong way. Go this way. Okay, equivalent states. So two states are equivalent if they both have identical outputs and every input in those equivalent states leads to the corresponding equivalent state. So are there any equivalent states in this diagram? So the first thing you should look for, are there any states that have the same outputs? Well, the bottom two, turn right and F, these two states have the same output. And you notice that when I'm in these, so let's hypothesize that these two states are equivalent. And so that would mean that when they have an R, they both go to wall 2, so that part is good. When they have a not R, they both go, if these two states are equivalent, they both go to themselves, right? So as it turns out, these two states are in fact exactly equivalent, and we can change this 5-state diagram into an equivalent 4-state diagram. And by equivalent, we mean it will, in all circumstances, the sequence of outputs given a particular sequence of inputs will be the same. We can't distinguish the behavior of the ant with this FSM versus the other one. Okay. We can certainly encode all of this stuff in the transition table. I'm not going to go through line by line how this works. Here's the entire transition table. I can, for instance, to compute the next state logic, S0 prime and S1 prime, that's this column. I can build a Carnot map and, draw patches and come up with logic equations for the next state. I can do the same for the outputs. And in fact, here's my 2 state bits, and here's my combinational logic cloud that's computing both the next state and the output values. So this is the entire schematic of a robotic brain, of a robotic ant. We're going to make a fortune next Christmas. Okay, so and so all the behaviors that you see all these things doing really can be captured using this sort of design methodology. Any sort of sequential logic, we can use this design methodology. Now I want to spend a few minutes, the last 6 minutes in the lecture, returning to an issue that we've been carefully ignoring, which is the fact that mostly when we design one of our pieces of sequential logic, we're very careful to set all the timing right and to check all the constraints about the setup and hold times and all the internal registers to guarantee that we meet the dynamic discipline. However, when we use an FSM that's connected to the outside world, like an electronic door lock, where the user who's busy putting their fat finger on my combination button isn't doing it knowing what my clock is like. It doesn't know, don't press now, you just ruined, you violated the dynamic discipline. You caused the input to change in such a way that we didn't meet the setup and hold times of those internal state registers. Okay, so we have this sort of fundamental problem, which is we need to come up with a strategy for dealing with real-world inputs that are impacting our clock state machine, because that's honestly most of the machines we build interact with the asynchronous real world. The real world where events are happening in such a way that they're not timed in any particular way with the rising edge of our internal clock. That's what we mean by asynchronous. Okay, so let's see if we can build this magic blue box here called a synchronizer. So the synchronizer basically takes an unsynchronized signal and produces a well-behaved signal that changes only after the rising edge of the clock. So this is going to be a magic device in here, a little something that's going to solve our problem of taking asynchronous inputs and producing synchronous, legal digital logic values. So this is called the bounded time synchronizer, that blue box. Here's the specification. So the specification is really pretty straightforward. If the input changes a certain amount of time before the rising clock edge, and there's a sort of allowable error. So if we're far enough away from the clock edge before it, we want the system to output, if we raise the input high, we want the system to output a 1. That's the synchronized value of that input. If the input changes some amount of time after the rising clock edge, like so, if it's low here, we want the logic to output a 0. And because we're not particularly interested in doing anything fancy, if the input changes within that window of close enough to the rising clock edge, we don't really care what the system does in terms of whether it's a 1 or a 0. But we do care that make a choice. Flip a coin, do whatever you want. Whatever you're going to do, output a value. Okay, make any arbitrary choice. So this seems a very generous specification. If it's obvious that the value is a 1, output a 1. If it's obvious the value is synchronized value should be a 0, output a 0. And if it's too close to call, pick a value and output it. As it turns out, we cannot build this system. We cannot. We cannot build a system that we can guarantee will work with 100% reliability. This is an unsolvable problem. Okay, and the difficulty turns out to be this sort of don't care case. And the difficulty with the don't care case is we cannot build logic that will guarantee to output a digital value. Okay, what we'll discover is our systems will have a behavior where it will not, in any bounded time, we can't guarantee it will make an arbitrary choice. We can't build the system. Now, if you were sort of paying attention and thinking about setup and hold times and registers, you might be tempted to build in one of these synchronizer things just simply using a D register. Here's the clock signal here, and we put the input into there. And so obviously if the signal in is valid T in, T setup before or T hold after, the register will behave correctly and the synchronizer will work. The don't care case that I sort of was hinting was the problem is what happens when in changes so as to violate the dynamic discipline of the register. We violate the setup and hold times. Okay, and so we're sort of lured by the digital abstraction to assume that the star signal here, the one that's after the master latch, will always be digital. And that's where we're wrong. That's where we're wrong. As it turns out, there are situations that can arise that, depending on when in is changing and when the gate signal, or in this case the clock signal, changes, we can get a situation where there's a third type of output we can get that's neither a 0 nor a 1. And that has to do with this magic third solution to the voltages on this feedback loop. So we had this feedback loop, right? Remember that? And we had this is sort of the voltage transfer curve of the V in versus V out curve of this feedback loop. Here, of the logic inside of the mux. Here it is here. It's a high here will produce, when the gate is low, a high here will mean a high here, and a low here will mean a low here. So that's this state and that state. But there is this intermediate voltage right here, this metastable voltage, where in fact the system will balance. It's unstable in the sense that as soon as it balances, goes by noise or something, gets perturbed slightly off this point, it will quickly, go down to one of the two, or go to either of the two stable states. But the system can balance for an indefinite time at that point. So if we go into storage mode, we change the input at such a time that when we go into storage mode, when we close this feedback loop, we're at this mysterious Vin equals V out voltage, this balance point. The system will be in what we call be in the metastable state, and will stay there for an unbounded period of time. Okay, so it corresponds to an invalid output level, so we're getting this sort of strange intermediate voltage out. It will eventually settle, but we can't put a bound on how long it will take to settle. So if it's metastable at a particular time, there's a probability that it will be still metastable some bounded time later is non-zero. In other words, we can never guarantee it. However, the longer we wait, the probability goes down exponentially that it's still metastable. So that brings us to the following solution, which looks like this. What we're going to do is, this is the register that can go metastable because in violated the dynamic discipline of this register. We're going to quarantine that value and simply give it a whole clock cycle to become unmetastable before we look at it. And because we've quarantined it for a nanosecond or 10 nanoseconds, whatever our clock period is, the probability that it's still metastable 10 nanoseconds later can be quite small. And in fact, if we're concerned that we haven't waited long enough, we can extend the quarantine time with additional registers. And so we can make it so the probability of being metastable on the final output here is as small as we want it. Okay, so we're going to solve metastability with these so-called pulse synchronizers. They aren't guaranteed to work, but we can engineer them to have a probability of failure that's once every 100 years, which is good enough. Alrighty, I'll stop there. Good luck with Lab 1 and your studying for quiz on the Friday.